Hi everyone, welcome back. In this particular video, we're going to go over the Friedel-Crafts alkylation reaction. This is an electrophilic aromatic substitution reaction that is useful in synthesizing alkylated benzenes, which basically means you can install an alkyl group on the benzene or another aromatic compound when you extend it to other molecules. So in the specific case of benzene, I have an example over here. So this example, we are reacting benzene with isopropyl chloride or 2-chloropropane. That's what you're reacting it with. So 2-chloropropane. And your product that you get is isopropyl benzene. And so essentially what you notice is that in this reaction, we are replacing a hydrogen on the aromatic ring, which is benzene here, with the alkyl group of the molecule that we are using. The alkyl portion of the molecule is installed on the benzene ring. And this reaction needs a catalyst. The catalyst is similar to what we've seen before. So if we're using chlorinated alkanes or alkyl chlorides, then the simplest catalyst that we can use is aluminum trichloride. Now, aluminum trichloride works here by activating this alkyl chloride in a manner similar to what we saw in case of a chlorination reaction or a bromination reaction. So essentially, the alkyl chloride here, this can interact with the aluminum trichloride by donating electrons to the aluminum. And this is going to give us an intermediate where now the chlorine would have a formal positive charge. The aluminum would have a formal negative charge. So you generate this intermediate, and from this intermediate, the bond here can break. So the bond between the alpha carbon and the halogen is what we are breaking. So the alpha carbon and the halogen. And that's probably something to notice here, that carbon is what's connected to the benzene ring in this particular example. But we are going to see some deviations here or some exceptions depending on the alkyl chloride. But the bond between the alpha carbon and the chlorine breaks. And this would essentially now give us a carbocation plus the aluminum species, where the aluminum has 4 chlorines connected to it. So it gives us a carbocation, which serves as the electrophile in this particular reaction. So the carbocation that's generated is the electrophile in this reaction. Now, since this reaction or the mechanism involves a carbocation as an intermediate, as an electrophile intermediate, what this means is the Friedel-Crafts reaction, this works best with secondary and tertiary alkyl halides. And that's because both secondary and tertiary alkyl halides, they can give you stable carbocations, relatively stable carbocations. Primary alkyl halides, on the other hand, are unable to generate carbocations. Okay, they're unable to do that. But even then, some reaction of primary alkyl halides with benzene have been noticed. So for example, you can react benzene with ethyl chloride. Okay, this is a primary alkyl halide now. So you can react benzene with ethyl chloride using catalytic amount of aluminum trichloride. And under these conditions, ethyl benzene is produced. So this is the organic product. We make ethyl benzenes. So for such examples where a primary alkyl halide can still give us an alkylation, it is believed that the intermediate that is formed looks something like this. So you have the alkyl halide, very similar to what we had before. This interacts with the aluminum trichloride, the catalyst. So the chlorine can attack this, and it gives us the intermediate where the chlorine has a formal positive charge and the aluminum has a negative charge. So very similar to the intermediate that we made here. And notice this carbon here is the alpha carbon. So in case of primary alkyl halides, what we think happens is that this intermediate that's formed, this serves as a source of the electrophile. So the carbon here, the alpha carbon here, serves as the electrophile in the Friedel-Crafts alkylation reaction. You do not generate, or you do not produce a formal carbocation under these conditions. So that's sort of like something different about the mechanism of the reaction. But we haven't talked about the entire mechanism here, so we will look at the mechanism next. So as we discussed earlier, the mechanism of this reaction involves the formation of this carbocation, which serves as the electrophile. Once the carbocation is formed, so the mechanism sort of starts here because we have to show the formation of the electrophile. So after these initial steps, and once the electrophile has been generated or produced, the rest of the mechanism is very similar to what we've seen with other electrophilic aromatic substitution reactions. So we have the carbocation, which is our electrophile. So the benzene ring serves as a nucleophile and attacks that carbon, which was the alpha carbon in our alkyl halide. And this is going to produce the intermediate, which is the sigma complex. So we get the sigma complex here. And the sigma complex is resonance stabilized. So keep that in mind. Let's show the resonance here. So we can use the pi bond. Sorry, this electron push needs to point there. So we can use that pi bond to show resonance. Get a double bond here, double bond here. The positive charge is here. Isopropyl group, hydrogen. This pi bond moves again. And we got double bond here, positive charge, isopropyl group, and the hydrogen. So those are all the resonance forms for this sigma complex. And at this point, or any point, actually, you do not have to show these resonance forms, but any of these resonance forms can be deprotonated by a weak base in the system. And since we have this aluminum trichloride system here, we're going to use that tetrachloride ion. We're going to use that as our base here. So one of the chlorines here can go and abstract or deprotonate the sigma complex, and the electrons from this bond will go to the space there to restore aromaticity. So we can make the molecule aromatic again. We get our product, which is the isopropyl benzene. Along with that, you will have HCl, and we would have regenerated our catalyst. So the aluminum trichloride catalyst is regenerated in the process. So that's the mechanism of the Friedel-Crafts alkylation. So in this part of the video, we're going to talk about some of the limitations of the Friedel-Crafts alkylation reaction. Although it's a great reaction at alkylating aromatic compounds, which means installing an alkyl group on an aromatic framework, the reaction has some limitations. One being that it works only for alkyl halides. And I want you to read this as an alpha carbon, which is sp3 hybridized. Okay, so we need something where the alpha carbon is sp3 hybridized. So in the example that we looked at before, we used an alkyl halide because the alpha carbon was sp3 hybridized here. The Friedel-Crafts alkylation reaction does not work for vinyl halides or aryl halides. So it does not work for these compounds. And that's because in the vinyl halide, the alpha carbon is sp2 hybridized. So this is where the alpha carbon is part of a double bond. And for aryl halides, the situation is the same because the alpha carbon is sp2 hybridized. So it doesn't work for such compounds. The second limitation is polyalkylation. Poly means many, alkylation, Friedel-Crafts alkylation. So you might see the installation of more than one alkyl group in some cases. So, and that's because the installation of one alkyl group, so when we do this reaction and one of the alkyl groups is installed on a benzene, or once you've added one alkyl group on the benzene molecule or that substituted benzene molecule is now activated. It is for doing the Friedel-Crafts alkylation reaction. So it would do the reaction faster, much faster than the original benzene molecule. So it is possible that you start with benzene and you're trying to add one alkyl group. So let's say this tert-butyl chloride using the aluminum trichloride, but your product may be like a dialkylated product. The installation of one alkyl group on the ring makes subsequent alkylations easier or faster. And we call this the activation of the ring, activation of the aromatic ring, which basically means that compound reacts faster than benzene itself. And then the third limitation is the possibility of carbocation rearrangements. Since the mechanism involves the formation of a carbocation intermediate, it is possible to expect rearrangements happening. So for example, if you react benzene with an alkyl chloride like that, where notice that the alpha carbon is secondary in nature, and adjacent to it, there is a tertiary carbon in your molecule. And what we know is that tertiary carbocations are more stable than secondary carbocations. So in this particular case, when you do the reaction, you might see product. In fact, this may be the major product of the reaction, where this tertiary carbon is what gets connected to the benzene ring. And that would only happen if the carbocation was at that tertiary carbon. So what could potentially happen here is that when that alkyl halide, so when we take this alkyl chloride and this interacts with the catalyst, the chlorine attacks the aluminum, or it shares electrons with the aluminum. This would give us the intermediate, where we have the chlorine with a formal positive charge because it shared its electrons with the aluminum. The aluminum has a formal negative charge on it. And this intermediate is what gives us the carbocation. So the bond between the alpha carbon and the chlorine breaks, and this is going to give us a carbocation intermediate plus the aluminum tetrachloride ion. And now this carbocation is on a secondary carbon, and right next to it there is a tertiary carbon. So this hydride can shift. So we can see a hydride shift happening. And so essentially that will give us a new carbocation where the carbocation is now tertiary in nature. So this carbocation is now tertiary. You still have the aluminum tetrachloride. And so now this, because this tertiary carbocation is more stable, this rearrangement, the hydride shift is going to be very favorable. And so that's why when you do the reaction, you would get the product where it's this tertiary carbon that's connected to the benzene ring in your product, or that's going to be like the major product of the reaction. So those are some limitations of the Friedel-Crafts alkylation reaction. But overall, the reaction is useful in making alkylated aromatic compounds. I hope you find the discussion useful. Bye.